All righty. Hi guys, how's everybody doing out there? A bunch of you guys are coming in as guests, and I don't mind, but it seems like for me, as long as I start my day by going to utexas.zoom.us, that seems to be the portal that works for me. Or the other one that works for me is if I go to Zoom, if I go to Canvas for this course, and then I click on Zoom, then it shows me all of my meetings. And I can just click, and I'm not sure why you're coming in as guest. Other faculty members have been reporting the same thing, that their students they have to go through some trouble and get admitted by the faculty member. Anyway, how are you guys doing? Do you have questions about the new homework that I've set up for you? Any of the problems that you've started working on? Of course, a lot of the stuff in there we haven't even started, but we are at least doing path integrals. We're trying to make sure that you guys understand the path integrals. No? No questions? All right. I'm going to give you more of the details on there, make sure you guys are understanding what it is that we're computing. And I want to work through an introduction to what surface integrals are in the same setting. If you have started reading ahead, you notice that there's also references in the book to vector fields. They're coming back. Oh, I don't want to discuss those yet. I'm skipping over those sections until the beginning of next week. So I actually got a little ahead today, and I made up some slides in advance, so I'll be able to give you what I hope are slightly better looking slides this time around. Also, let me just apologize in advance because I'm in a townhouse where we share a wall with a neighbor, and those neighbors have decided to renovate their bathroom, and so there is some hammering and drilling and stuff going on. If there's too much noise at any moment, just raise your hand or yell something out, and I'll repeat or try to clarify. All right, let's get going with these integrals. So that seems pretty good. Okay. So here's where we've been for a little while. We're discussing integrals, and every version of our integration problems has got the same framework. Somebody gives you a set and a function defined on the set, and they ask you to compute an integral, and it always means this. Somehow you have to split the set S up into little pieces. Pick a point in each little piece and evaluate the function f there, and multiply that by the size of the piece. You add that up over all the little pieces, and you've got something that more or less approximates what you meant to calculate in the first place. It'll be an approximation, but the approximations will grow better as the pieces grow tiny. So it's some kind of limit like that. So that's been a constant throughout all of our discussions. Some applications of this show up in a natural way when, for example, this function that you're trying to integrate is a constant, because then it doesn't matter where you evaluate the function. The value of the function always turns out to be the same number c. And then you'll be multiplying that same number c times the size of every piece. So when you compute your sum, you'll have a constant factor that you can pull out. And you'll just be taking the sum of the sizes of the pieces. Of course, you can then pull the constant outside the limit too. And so you'll have something like this. It'll be c times the limit of the sum over all pieces of just the sizes of the pieces. But of course, if you add together the sizes of the pieces, you get the size of the whole thing. And then it doesn't matter how big the pieces were in the first place. Taking a limit won't change anything. So you'll just get c times the size of the set S. And in the special case where the constant is 1, That tells you can get the size of the set S by just integrating 1 over the set. And that covers some examples you know. I mean, if I had gone to you and when you were taking Calc 1 and said, what's the integral of 1 over an interval, you would have probably found an antiderivative, which is x. I'm sorry. And you evaluate x at the two endpoints and subtract, you would have gotten b minus a. And then when you were done, I would have said, you know, b minus a is in fact the length of that interval. And now this semester, we've been using this idea to calculate areas. You can get the area of a chunk of the plane by integrating 1 over that chunk. Same thing with volumes. These kinds of integrals now, with the left-hand side, we've been evaluating them with the help of the change of variable theorem. So it's made things go a little more smoothly. But now, in the context of path integrals, I want to do the same thing when the set S is a curve in the plane, or even a curve in three-dimensional space. Integrating 1 with respect to length, that means that if I measure the size of each piece, meaning the length of that piece, then I'll get the overall length, or you could call it arc length, of the total curve. So this concept of integrating something simple like 1 over a stranger set like a curve in the plane or a curve in three-dimensional space, it obviously has applications for us. But you do run into the question of how exactly am I supposed to split a set S, a curve like this, for example? How do I split it up into smaller pieces? And then once I do that, how do I even compute the size of that piece? I mean, it's not hard to visualize splitting a curve up into smaller curves, but asking for the arc length of a little piece so that you can get the arc length of a big piece sounds like you're sort of going around in circles. It's called begging the question. But I have an idea. And the answer to this is to parameterize the curve. So if you find a parameterization of a curve in the plane, what that means is a function that tells you where you're supposed to be, where in the xy plane you're supposed to be at all times t. That's how we've interpreted what a parameterization means. The curve is the roadway. The parameterization is an itinerary. It is a set of directions that tells you at each moment in time where you're supposed to be. But now geometrically, it is a function that's carrying a small interval of time over to exactly the set of points you're supposed to get to. And that makes it easy to partition the curve up into smaller curves. You just partition your interval of time into smaller intervals, and then you figure out what part of the curve you've traveled on for each one of these parts of your interval of time. Here I've broken my interval of time up into 3 smaller parts of time, and that gives me 3 smaller arcs. And when I go through the business of trying to integrate a function over this curve, I have to select a point inside each one of those little arcs. But of course, the natural way to do that is to just select a point in each one of these little intervals of time and say, okay, we'll take, for example, the middle of that hour or minute or whatever the little interval of time is, take that moment in the middle, use phi to figure out exactly where you are on the curve at that moment, and that'll be the point on the curve where you evaluate the function f. You should notice that at that point, you're actually taking a composite. You're starting with a point on this interval of time. You're applying phi to that first to get a point in the xy plane, and then you're applying the function f. You're evaluating the function f at that point in the xy plane to get some real number. That's the number that's going to go into these formulas. So really what you're doing is you're evaluating f composed with phi. That composite function is being evaluated at these points on the t-axis. All right, so the parameterization gives us an answer to the second question of how are you going to split up the interval, split up the curve into some smaller curves. But it also will give us a hint as to how we're going to evaluate the sizes of these pieces. I'll show you that in a second. I'll be able to estimate what the sizes of these pieces are by knowing the sizes of the pieces that they were parameterized by. And I can do that for curves in the plane. That's what I've been pointing to in this discussion. Nothing different really changes when it's a curve that winds through three-dimensional space. Now, if nobody has a question about what I've said so far, let me point out that the same concept can be used to help us integrate over surfaces. Specifically, imagine you've got some wavy surface floating around in three-dimensional space. If you're worried about how to chop it up into little pieces, pick a point on each one of those pieces and then measure the size of each of those pieces. Let me suggest that you use a parameterization, which I will call capital T. That would be some function that goes from the plane and carries each point in the plane to a point in three-dimensional space. If you use, let's say, U and V as your coordinates in the plane, and X, Y, and Z in your coordinates in three-dimensional space, then you need to specify functions of U and V for all of the X coordinate, the Y coordinate, and the Z coordinate. But then if you apply this function capital T to all the combinations of U's and V's in a certain region, that'll give you a lot of combinations of X, Y's, and Z's that all lie on a surface. Now in this picture, I set it up where the domain is a rectangle in the UV plane. It doesn't have to be a rectangle. It could be any shape in the UV plane, but in practice, you probably want this to be something fairly simple, a rectangle, a triangle, a disc, something like that, so that you can actually make use of this process to evaluate some integrals that were done on the surface. And you see I split this into a 3x4, this big rectangle into a 3x4 grid. That gave me 12 little pieces in this picture. So you should get in the habit of thinking of this as a one-to-one correspondence here. Capital T takes each of these little patches and it twists it and bends it a little bit to give you a curvy patch of the surface in three-dimensional space. When you have to select a point in that little patch, of course, the way to do that is to just select a point inside this little rectangle and then figure out where capital T sends it. So capital T will carry this point over to that point. And then if you want to evaluate the function f right here, effectively what you have done is you have evaluated the function f composed with t here. F composed with t starts here, first applies the function capital T to land here, and then it applies the function f to land somewhere in the real number line. So that will be how you evaluate the function f at different points on these different pieces of the surface. You'll evaluate f composed with t at these points inside the UV plane. But we have still the question of how do I get the size of this curvy piece? How is that related to the size of the nice little rectangular piece that I had over here? It's not easy, but it's not beyond us. We'll be able to get that. All right, so what I want you to see is I've got a similar setup for both curves in 2 and 3 dimensions. Those are parameterized by intervals, and surfaces, which can be parameterized by rectangles or other subsets of a plane. And you'll notice I didn't talk about this today, but you see here what kind of fills in the grid of little illustrations. Here you have it's a surface that's already in two-dimensional space. But you could imagine the issue of trying to integrate over this and saying, how am I going to partition it? How am I going to select my points? How am I going to measure sizes? That comes in exactly the same way that I did it over here. You just need to parameterize this set with some prettier set inside the UV plane. A parameterization is just a function that now goes from R2 back into R2. So this is the setup for what we have been calling the change of variable theorem, at least in the plane. So if you're comfortable with the change of variable theorem as it is, I don't want to change it, but I do want you to see that if you can extrapolate a little bit, you'll be able to see that what you've already done for the change of variable theorem will also let us compute integrals over surfaces. We'll be able to compute, for example, areas of surfaces that float in three-dimensional space. All right, I'm going to save the surfaces for later. I want to make sure that we're good on the curves first. All right, so let's do that. So let's answer the question of how are we going to compute the sizes of the pieces that we've split our curve up into. My proposal for how to make the split seems straightforward. You split this interval and then you watch for where things get sent. But how exactly do we calculate the length of those little arcs? And I'm going to do that by making two approximations. Both of them are messing up the answer a little bit, the answer of the question of how big is that piece. But in the limit, when you take this partition of the interval on the left side, when you take that to be finer and finer, both of the little approximation errors that I am introducing will get smaller and smaller. So here I am. I've used a magnifying glass to zoom in on a tiny little interval on the t-axis. That's on the left-hand side of my parameterization picture. That's in here. And I'm applying phi, my parameterization function, to all the points between the left edge and the right edge. I've called those numbers T1 and T2. They're just 2 points in R1. And phi carries each one of them to some point on this path, on this roadway. Phi of T1 is up here, phi of T2 is right there. Now, I said I'm going to do two things to approximate the length of this arc. The first thing is to realize that if you have chosen the T1 and T2 really close together, then the function capital phi doesn't have very much chance to make this road be very twisty. In a small amount of time, you can't go on a very twisty road. You're going to have to go more or less straight. In any small interval of time, you're going to go practically along a straight line. So in other words, what I'm doing as my first stage of the approximation is I'm going to replace the true arc length of the curve that goes from phi1 to phi2 by just the straight line segment that goes from phi of T1 to phi of T2. Okay, I know they're not the same, but the difference will disappear when I go to take a limit where the T2 and the T1 will be closer and closer together. So I need to find out how far apart phi of T1 is from phi of T2, knowing that T1 and T2 are really close together. Now, the second stage of the approximation is to say, we addressed that kind of issue at the first half of the semester. That's exactly what derivatives were for. The whole point of derivatives is that they gave us ways of at least approximating how the value of a function changes when you change the input a little bit. See, this is the kind of formula we wrote down at the beginning of the semester. If you want to know exactly where phi of T2 is, I can't tell you, but I can estimate where it is because the point T2 can be thought of as a small displacement vector away from the point T1. Now, it's not a big deal to talk about vectors because this is all taking place in the real number line. A vector is just a left to right displacement. But I'm going to be talking about vectors in a few minutes anyway, so let's just get in the habit of describing it that way. This point T2 is a small displacement vector away from the point T1. So I will write T2 as being T1 plus a small displacement vector. What we said in the beginning of the semester is if you didn't go too far away from T1, then the value of phi here shouldn't be too different from the value of the phi there. So phi of T1 is my, well, I guess I would call it my 0th order approximation to the correct answer of where is phi of T2. But the first order approximation, the interesting part is you move away from this point phi of T1 by a small vector to get to, or at least close to, phi of T2. I'm not actually going to be able to figure out this dot, but I'm figuring out where this little star is. This little star is the thing that I'm computing here after the squiggly equal sign. It's almost the same as phi of T2. But this one is an easier one to compute because it uses the formula from our discussion on first derivatives. The displacement between phi of T1 and this point that's shown as an asterisk, that displacement is the same as, well, you take the displacement vector v over here in the domain and you multiply it by this matrix. That's what the role of the first derivative as a matrix was for us at the first half of the semester. It's a matrix that tells you how to finagle the vectors. You take your displacement vector in the domain and you multiply by this matrix to get the displacement vector in the codomain. If I use this formula, then I'm really in great shape to start to talk about the missing piece of the puzzle, where I said, what's the size of a piece of this arc? The length of the arc is almost the same as the length of the straight line segment, meaning the distance between those 2 points. But the straight line segment that goes between these 2 points is almost the same as the straight line segment that goes from this point to the nearby point. And that'll be the length of the vector that joins those two, which is this vector right here. Okay, so my formula for the length of this arc, I should say the little arc length, the formula for that little piece of arc length is it's approximately the length of this vector. This is the vector that you get by multiplying the vector on the input side by the first derivative matrix. Now I'm going to use that formula again, and when we get to surfaces, I have to talk about how we're going to handle this in more than one dimension on this side. But for us right now, if phi is a function that goes from R1 into R2, that means that the phi prime of t at each point will be a 1 by 2 matrix. If it goes from R1 into R2, it'll be a 2 by 1 matrix. That's a column matrix with 2 entries in it. So this right here is actually a column of 2 numbers. The 2 numbers that you get are, you use your parameterization function to express both the x and y coordinates of any point as functions of t. So you've got 2 functions of t, one for the x coordinate, one for the y coordinate. You differentiate the first output coordinate in the first row, you differentiate the second output coordinate in the second row. And since you have only one input variable, you'll only have one column of derivatives. So this here refers to that column matrix. It's got the derivative of the first function, the first component of phi in the top, second component of phi in the bottom. And you'll take that column matrix and you'll multiply it by this little vector. Well, that vector just goes across the real number line. It's just a number. It's just telling you how far T1 and T2 are apart. So when you ask for the length, I would say, oh, well, gee, you're asking me for the magnitude of a vector, but that vector is a scalar multiple of this column vector. And then the magnitude of a scalar multiple of a vector is just that scalar times the length of the vector that came first, before the v. And the scalar involved here is this number v, which is the length of this little interval. It's the distance from T1 to T2. So that's the length of the little piece that I divided my big interval up into in the domain side. So when I split this one up into a few parts, and that gave me the corresponding split over here, then I'm figuring out the length of this little arc by taking the length of the corresponding interval here, and I'm multiplying it by this fudge factor. So this gave me the thing that I called just fact for you guys last time. I said that when you are computing an integral, a path integral, and using a parameterization phi, you'll know that you need to evaluate the function over here instead of over there. That's why there's a composite with phi in there somewhere. But there's a fudge factor, a stretch factor, that talks about how phi is multiplying the lengths on the domain side to give you lengths on the output side. And the formula that I said would be the fudge factor is exactly this first derivative. I'm sorry, it's the magnitude of this first derivative vector. Somebody's asking, is this the gradient? It's not a gradient, really. The gradient would be a 1 by 2 matrix. The gradient shows up when you have a function that goes from R2 into R1. This one goes from R1 into R2. So it's actually the magnitude of a column matrix, the size of a column matrix, not a row. But you compute magnitudes in the same way you've always computed the magnitude of a vector, so I wouldn't stress over the difference. All right, so just to use this piece of information, this is going to help us now evaluate any integral, any path integral. If you want to integrate a function over a curve, you know what the general definition is. You're supposed to chop it, multiply, add, take a limit. Same thing I always say. But now what we've just said is that the sizes of those pieces can be calculated as the sizes of the corresponding little intervals multiplied by this fudge factor. Now, the value of the fudge factor can be changing when you move from one little interval to the next. So you see me evaluating phi prime right at the point T1, or you have to evaluate phi prime somewhere on this interval. So this value of the fudge factor might be different for different little intervals on the T side. But whatever they are, this will give you a function of T that adjusts these sizes to turn them into those sizes. The other factor, as I said before, you evaluate the function f on the curve. Well, effectively the way to do that is to evaluate this function f composed with phi. It's a two-stage evaluation process. You start on the interval, phi carries you to the curve, and then f evaluates the function. So we put these three factors in where there used to be just two, and then add all the products together. You're taking a limit when your pieces get smaller and smaller. These are now pieces of some interval on the t-axis. But when you read it that way, now lump these two factors together and say, well, this is some giant function of t, and you're multiplying values of that function of t times the sizes of little pieces of the t-axis. So you're computing an integral, I guess it's an integral with respect to t, of this function. That's the function that's now being integrated across that interval that you used to parameterize your curve. So this is the recipe for how we compute path integrals in general. Give me any function f to integrate over any curve. I've talked about it as if the curve is in two-dimensional space. It can be in three-dimensional space just as well, in n-dimensional space for that matter. I don't care. But you'll always evaluate this by simply computing an integral of a Calc 1 type of function. It's an integral of a function of one variable integrated over an interval, and this is the function you integrate, where phi is a parameterization of your curve. So that's just a little reminder that you're not going to get anywhere in these problems until you remember how you can parameterize a curve. So let's do an example. Here's the example. I want you to look at the curve y equals x cubed, y squared equals x cubed rather. It obviously passes through a couple of points, namely 0, 0 and 1, 1. Both of these points have x and y coordinates that pass this membership test. So they're on this curve. Oh, it's a curve, by the way. One equation in two variables. 2 minus 1 is 1. Should be a one-dimensional set, a curve. So I just want you to join them, however the curve joins them, and tell me what is the length of the arc that joins them. It's got to be at least square root of 2, right? Because that would be the straight line distance between those two. But exactly what is it? I don't know. So let's try to figure that out. Our general recipe for getting the length of a curve is you can just integrate the constant function 1 over your curve. But how do you actually carry that out? Well, you will find a parameterization and you'll compute this composite and you multiply it by the stretching factor. That's phi prime of t. and you integrate that with respect to t. And fortunately for us, in a simple question like this, when you form this composite, you're always just going to get a a constant function composed with anything. It always just is that same constant function. So I don't have to worry about that part, but I've got something here that has a phi in it and something over here that refers to phi. This is going to be the domain of the function phi. And I don't have a parameterization. I need a parameterization. Somebody's got to help me out here. So you have to find a parameterization of the curve that was given in the first place. Well, guys, I knew this point was coming in the semester. I knew it at the beginning of the semester, and that's why we spent a lot of time messing with this little triangle. Remember that? A curve or a surface or more general geometric sets can be described in, well, lots of ways, but generally they're either given explicitly, implicitly, or parametrically. In our setting, this particular curve was already given implicitly. It's the set of points where some function of two variables stays constant. It's equal to 0. This is a level curve of a function of two variables. I moved everything to one side of the equation and I said I just need some expression involving x's and y's to stay constant. That's not good enough to do this kind of a calculation because I need a parameterization. So I want to somehow go from right to left along the bottom edge of this triangle. And I don't, in general, have a way to do that. To get a parameterization, you would need a function of one variable that spits out two output components. I need to express x and y as functions of t, and I mean, there's no t's in here. How am I even supposed to get t's mixed into the problem? So the route that I have suggested earlier in the semester is that there is a quick way to go to the third vertex of the triangle, which is to give the curve explicitly. Now, to give the curve explicitly, you're supposed to write y as a function of x. In just 3 or so words, how do you change a curve given implicitly into a curve given explicitly? What's the process that lets us move up this side of the triangle? No takers? What I wanted you to say was solve for y. Oh, there, somebody said it. Diego, thank you. Yeah, you express one of the variables in terms of the other. You can go either way. I said here express y as a function of x. You could have solved for x as a function of y. That's also fine, okay? So to give a curve explicitly means to find a function of one variable. This one goes from R1 to R1. You need a function of one variable whose graph is the curve. So, well, algebraically, it's very easy to do in this case. If you want to solve for y as a function of x, you just get y equals x to the 3 halves. And so that little part of the journey along the triangle is easy, but it's also useful because there's an easy way to go from this corner down to that one. If all else fails, if you have a curve that's given explicitly, you can parameterize it by simply letting x be equal to your new parameter. Let your parameter be called t, then your parameterization just begins by saying let x equal t. Of course, then this formula tells you that y is going to have to be something else. It'll be whatever it has to be. If x is a synonym for t, and you need y to be x to the 3 halves, then here you should write that y is t to the 3 halves power. So you guys are going to have to do something like this in every one of the path integrals that you compute. You have to start by finding a parameterization. Once you have a parameterization, then you'll be able to start to write out the formulas as I was using them in the, well, here, this was the thing that we said we needed to use. So the formulas that I've written down for you here specify that x and y should be the first and second components of this function phi. So this phi maps from R1 to R2. Every point that it gives you as an output has x and y coordinates, and the cube of your x coordinate and the square of your y coordinate, they will be equal. So you're always going to get points on that curve course, you do have the question of how do I get just the points on the curve that are between those two? And in order to do that, you need to know the range of t's that work to give you this point and that point. I guess it's clear if these are the formulas that you're going to use, that the one and only one time that you will pass through the origin is when t is equal to 0 and t to the 3/2 is also equal to 0. So t equals 0 is what you need to start here. And you will get to this point exactly when t is equal to 1 and t to the 3/2 is also equal to 1, which is to say you will get here at time 1. So your range of variables, your range for the variable t is that t has to range between 0 and 1. So that is the interval that goes down here. And what's going to go up in this spot will be the vector phi prime of t, where this is showing you your position at all times t. If this is your position at all times t, phi prime can be thought of as the velocity vector, and you want the speed, the magnitude of that velocity vector. So I can compute the velocity vector for you by just differentiating both of these components. I've done that here. There's the derivative of t, here's the derivative of t to the 3/2. So there's my velocity vector, and you guys know how to compute the magnitude of a vector. That's just the square root of the sum of the squares of the two components. And integrating this over the interval from 0 to 1 means that you just have to compute a Calc 1 type integral. Integrate that function from 0 to 1. I guess you can probably see that that's not a hard one to do with the u substitution. This is what I would use. I would let u be exactly what's inside the square root symbol. So the du is 9/4 of the dt. And now I substitute out all the t's and put u's in their place. You could change your limits of integration first. If t used to go from 0 to 1, then u goes from 1 to 3/4. Your function of u over here is simply, your function of t now becomes a function of u, which is just the square root of u. And here our calculations give us a way of transforming this differential into that differential. It's 4/9 of a du. So that's a simple integral now for a Calc 1 student. Pull the 4/9 out. Anti-differentiate this to get u to the 3/2 times 2/3. Stick in your limits of integration, and this is the number you get out. And I'm sorry I didn't evaluate this one numerically. I invite you to do that. This is a little more than 3, and if you raise 3 to the 3/2 power, you'll get something a little more than 5 or 6. So this difference is in the range of 4 to 5, and if you multiply that by oh yeah, that's right. Yeah, if you multiply that by a number between 4 and 5, say, you multiply that by this fraction, which is a little less than 1/3, then you'll get a decimal that's somewhere between, like, I don't know, 1.1 and 1.7. And I said at the beginning you expected an answer that was more than the square root of 2, which is 1.4. So we seem to be in the right ballpark. Let me point out that when you go through this process and you find yourself doing a u substitution like this, what that actually suggests is that you could have done a different parameterization that would have led you more immediately into exactly this integral that I had down here. You could say, wait a minute, if you know that u is equal to 1 plus 9/4 t, you can turn that around and write t as being 4/9 of u minus 1. So use this to substitute into the formulas that gave you x and y coordinates. If you do that, now your x coordinate is just 4/9 of u minus 1. And your y coordinate would be that quantity to the 3/2 power. That may not look like a spectacular parameterization, but it does work if you use u's that come from exactly this interval. I invite you to check this out. You are using a different parameterization on a different interval. And when you go through the process of computing the derivative, the magnitude of the derivative function, you'll find that that comes out to the thing that I called phi prime of t, or now it'll be phi prime of u. That magnitude, that turns out to just be exactly u. It'll be 4/9 of u. So that will lead to exactly the integral that you see here. And that's taking account of the general idea of how parameterizations and changes of variable work. Here you have some portion of the t-axis that was mapping onto this curve by a parameterization phi. When you did a u substitution, what you literally did was you took this range of t's and you wrote it as the image of this range of u's. There is a different portion of there's a different function defined on the u-axis. I guess I might call that a capital T because it's a change of variable. And it's exactly the function that you see right here. It gives the t coordinates as a function of a u coordinate. So when you put together what it is that a change of variable does, a u substitution does, together with what a parameterization does for you, you see that actually all you have really done is reparameterized the curve using a different parameterization, namely it's phi composed with t. So this would be a different parameterization. I wouldn't expect anybody on the planet to come up with that one. There is a different parameterization that you might have come up with for that same curve. If you need to have x and y be written as functions of t in such a way that the cube of the first function matches the square of the second function, I got a suggestion for you. Why don't you just let phi of t be t squared and t cubed? Because the cube of this and the square of that are both t to the 6th. And again, as it turns out, you need t's to go from 0 to 1 to get from 0, 0 up to 1, 1. So your length can be given by the same kind of a formula, which now when you compute the derivative, you get 2t and 3t squared. So your length vector has got a very different look to it. And you would end up using some very different algebra to simplify this. So you see, you end up with a very different integral. Now this integral is something you could again compute, and you should again get exactly the same number. It's got to be the length of that curve. I know how you guys would begin it. But the only point that I wanted to make with this example is different parameterizations will lead to the same answer, but by way of a very different looking integral. Some of those integrals easier than others. And therefore, if you decided to parameterize a curve in one way and you ended up with an integral that you don't know how to make progress on, what you should probably do is go back and see if you could find a very different way to parameterize the curve. All right. So now you have a recipe for computing path integrals. If you can parameterize them, all you got to do is use the general formula that I wrote out. I don't know where that page went. This one. This will help you compute any path integral of any function on any curve. If you can find the parameterization phi, you just compute a Calc 1 type integral and you'll have your answer. What I do want to go to next, though, is I want to start talking about surfaces. So what do you do if you have a corresponding problem where somebody wants to find out the surface area of a certain surface, or they want to evaluate the integral of any other function over some surface that's fluttering through three-dimensional space? Maybe the function is defined as a function of x, y, and z, but you only get to certain combinations of x's and y's and z's on the surface. You know that what that means is you're supposed to take the surface and you chop it up, and you multiply the values of the function times the areas of the little bits. Size obviously has to mean area in this context. So you're asking those questions we had earlier, which is how do you split up a surface and how do you compute the areas of the pieces? So you know what I said before. I said you should parameterize your surface with a function that is defined on some pretty region in the UV plane, mapping that into onto your surface that floats around in three-dimensional space. Now here's the thing, if you have such a division of your rectangle in the UV plane, you'll be splitting it up into tiny little rectangles that will each one of them be transformed by T onto a kind of a curvy shape that probably has 4 recognizable edges. I need to find the area of that kind of pillow-looking shape. That's hard. But I can estimate it in the same way that I made my estimates for lengths in the curve situation. And my estimate will involve a couple of degrees of cheating. One is I'm going to replace these, some of the corner points by other points that are close by. So just like last time, I have little stars instead of the true outputs. So I'm supposed to compute, if I call these corner points P and Q and R, and I didn't label that one, then they will separately be sent to T of P, T of Q, and T of R. But I'm going to replace those. That one will be fine, but I will replace these 2 corners by some nearby points that I'm going to call R prime and Q prime. So that's my first slight cheat. And the second slight cheat is I'm going to say, yeah, you know what else? I'm just going to take not the wavy patch that connects that point to that point and that point, but rather I'll just take the parallelogram that's floating nearby. It's a part of the tangent plane, if you will, the tangent plane to the original surface near P, T of P. And both of those cheats are introducing a little bit of error, but when the division into tiny rectangles here gets to be very fine, then the amounts of the cheats will go to 0 over here, so that in the limit, you will actually be computing sufficiently accurate areas of these little patches. All right, so my question then is, how am I going to get the area of that parallelogram patch? And I can do that by using, again, these ideas from first derivatives. You see, I'm going to, well, first let me tell you what the Q prime and the R prime are. What I'm going to do is, I'm going to find this point Q. That's at the corner of the little rectangle in the UV plane, and say, I got to Q from P with a small displacement vector. Now that vector ran straight across. It's a vector, so it's got 2 components, but the second component is a 0. If you write your vectors with angle bracket notation, this is the way you would write it. If you write your vectors with a column, this is the way you would write it. But du is a small number, and it tells me how to get from P to this other corner Q. All right, so the way I'm going to get this point T star is to use what first derivatives tell me is the approximate location of T of Q. If Q is a small displacement vector away from P, then T of Q is almost a small displacement vector away from T of P. And the small displacement vector that joins those 2 is approximately given by this derivative. Here's the formula, it's just like the one that I had earlier today on the curve. Since Q is a point that's close to P, it's exactly that displacement vector away from P. T of P plus a small vector will be approximately T of P plus, and here's how you get your displacement vector on the surface. You multiply this derivative matrix by the column vector of how far you displaced yourself in the domain. That's the role of the derivative. That's why our derivatives are matrices in this class. It tells you how to rotate, how to twist and stretch a displacement vector in the domain to get the displacement vector in the codomain. So this long thing is the point that I'm calling Q prime. It's not quite where T of Q is, but it's close. It's close enough for our purposes. And it's a point that you start at the point T of P, and then you move away a small displacement vector. This small displacement vector, that tells you where to move to get to this point Q prime. In exactly the same way, this other corner of my little rectangle here is a point that I called R, and I get to R by starting at P, and I move straight up a small amount. Moving up a small amount means you've got a displacement vector that's got a 0 as its first component. You either write it as 0, comma dv with angle brackets, or you write it as 0 with it on the top and a dv on the bottom as a column vector. I don't care which notation you use, but when you want to figure out where the heck does the point R go under T, you estimate it by saying it'll be almost the same as this point called R prime. My R prime is what you have on the other side of this kind of very similar formula. In fact, it's identical to the formula I use for Q prime, except that I'm multiplying this matrix by the second displacement vector. Instead of this displacement vector, I'm using this displacement vector now. So, like I said, I'm cheating a little bit by moving these points around, and I'm going to cheat a little bit more by replacing the fluffy surface by a little parallelogram. But it's a close enough cheat so that the area of my piece that I need in the integration theory is going to get replaced by the area of the parallelogram. And you guys learned early in the semester how to compute the area of a parallelogram. The way to do it is you find the cross product of the vectors on the two edges and take the magnitude of that vector. So cross products are coming back, guys. Fortunately for us, those edges are not too hard to write down. Here they are. The edge is the vector that joins T of P to Q prime. It's the stuff you added to the T of P to get the Q prime. It's this vector right here. So that vector is your first edge. This vector is your second edge. And each of these edges is actually pretty easy. It's a scalar multiple du. That's a scalar. You're multiplying du times the vector 1, 0. And likewise, this is dv times the vector 0, 1. So if I pull out those factors, those scalars, when you are taking taking cross products or magnitudes, you can pull out scalar multiples. So there's those two scalar multiples pulled out. And all that's left is for you to take the cross product of the derivative matrix times the vector 1, 0. And then there's the same derivative matrix now multiplied by 0, 1. And if you guys remember what happens when you multiply a matrix by these very simple vectors, you might recall that all you're doing is you're picking out here the first column of the matrix T prime. And likewise, this one will be the second column of the matrix T prime. And now, if you think about how you compute a derivative matrix, remember you get one row of your derivative matrix for each of the output variables, x and y, or x, y, and z. And you get one column of your derivative matrix for each of the input variables, which in our case are u and v. So the first column of T prime is exactly what you get by differentiating your formula for the transformation capital T. Differentiate it just with respect to u. You'll have the partial of x with respect to u, partial of y with respect to u, partial of z with respect to u. And likewise for the second column, it'll just be the partials of x, y, and z, but just with respect to v. Each one of those will be a vector with 3 components. Take the cross product of those vectors, and what you will get will be a vector whose magnitude is the area of the little parallelogram that's approximating the area of my sort of pillow-shaped region. So this right here, this is the fudge factor that's going to go in. I know I'm over, but I'll write the formula anyway. To integrate some function over your wavy surface, that's going to be, you just integrate over your rectangle or whatever it was in the UV plane. And what you're going to integrate here will be first f composed with t so that you can actually evaluate the function at these points. And then the other factor is going to be this one. This is the fudge factor that says how much areas are changed by this transformation u. This is the area in the domain space, and all of this is the area in the codomain. So there's been a stretching by this much. All right, we're going to have to do examples on Monday, but I did want you guys to see that the surface formula is built on the same ideas as the ones we use for path integrals. So if you can do curves, then you can do surfaces. The formulas are obviously going to be more cumbersome, but the idea isn't really all that much more complicated. We'll have the examples on Monday, but do you have questions for me? Yeah, Yangshu, you do have your hand up, I just now noticed.
Yes, I want to ask the question about the previous section is about the curve to another.
Yes?
Yeah, I remember you use U to substitute for T, right?
Yes?
So in that way, you are first in T and then goes to U and then goes to XY, right?
Well, actually, the other way around. I think it's more fruitful to think of it by saying you start. I think I wrote this down.
Oh yes, you wait.
Yeah, you could think. I mean, you could. It's this picture here. Yes, I mean when I said let U equal something, I was actually giving you this transformation. I changed T's into U's, but as you saw up here, I then also changed U's, and I can write T as a function of U. So a change of variables is always a two-sided thing. You can go either direction.
Yes,
Parameters.
Yes, I noticed here when you goes from U to V, you actually just subtract, actually dividing the thing by the how do you call it, the length of the vector, right? You just divide it. But if you go another way around, you just times the length of the vector, right?
Yes.
Okay.
Yes, that's true. You can think of it that way. You're talking about the 4/9 minus the 9/4 versus
Yes.
the 9/4. Yes. I mean, it is true. I haven't mentioned this to you guys, but it is true that when you calculate the determinant of a T prime, that will be exactly the inverse, the reciprocal of the determinant of capital W prime, if you interpret them in the right way. When you have two functions that are inverses of each other, then their derivatives are inverses of each other as well. And then the determinants are inverses of each other.
Okay, thanks. Another question is that, at the beginning, the first chapter, when we compute the determinant for the first part, like, I'm questioning, like, what is the determinant has to do with the cross product, right? So, like, there is some connection, right?
Yes, if you look back at your formula for how you compute cross products, think of how you guys compute cross products. A lot of you liked doing that. Remember, you put your two vectors together, you put ijk across one row, you slap on a determinant symbol, and so now you're computing a determinant of a 3x3 matrix to compute a cross product. So you already had a connection on some level.
Okay, thanks.
Yeah, I don't want to hold everybody over, but so we will discuss more of this on Monday. I would like to do examples on Monday, but maybe you have enough information now to get started with some of the surface integrals on the homework. Okay, the vector fields, we're coming back to that on Monday and Wednesday as well. But for now, just don't worry about those. All right, guys, I'm going to call it. If you want to continue with questions or discussions, just meet me in the office hour, okay? Have a good weekend, stay healthy, and we'll see you on Monday.